Hello. Today we're going to talk about how to take the grade, rolling, and therefore the total resistance and use it to compute how much work we can do with a wheeled vehicle. So we're going to do this as just an arbitrary wheeled vehicle. We have that we're going to use today for our wheeled vehicle. We are going to use a 745 C articulated off-road truck. And we know that that vehicle has an empty weight that is equal to 74,100 pounds, and it has a loaded weight at its maximum capacity of 164,500 pounds. This is gross vehicle weight, this is gross vehicle weight, and you can see it carries about 90,400 pounds of stuff, whatever that happens to be. It could be steel shot, probably soil in this class, but it could be anything, right? Articulated truck means that it has a hinge. So if you look at the truck from up above, there's a hinge. And so this portion of the truck can turn a great deal independent of the rear portion of the truck, and that type of articulated truck very useful in off-road conditions because it can make very sharp turns, much sharper than you would ever need on the highway, so you wouldn't do it that way on the highway. We need to know a little bit more about our truck. It has a retarder, which is an automatic brake using the engine for going downhill. Now, why do you want it braked? Wouldn't you want to go downhill as fast as possible? Because it's all fun and games till you flip off the road. So you want to have some controlled speed, and the easiest way to do that is, rather than wear out the gears, is use the brake as the engine brake as a piece of information that, or a method of slowing the truck down so that it doesn't run away. We're going to roll this along a road. We have a section of road, runs 1,500 feet. It has a rolling resistance that is equal to 200 tons per axle. Give me a second, sorry. So we have a rolling resistance, and it's equal to 200 tons per axle. We have a grade resistance as well, and here we have a rolling resistance. Yeah, so it's 200 pounds per ton. And our grade resistance, this is a 0% slope, so our grade resistance is equal to 0%. Then we have a section that we're going to climb. It's going to be a little bit more complicated. This is going to climb at a 7% grade, and our 7% grade, we're going to run another 1,500 feet. And then we are going to go take a look, and we're estimating some of the properties of that section in terms of its ability to handle traffic or carry traffic. And if you give me a second, I'll tell you what that is. Maybe, probably. So that we can make sure I don't send you off the wrong path. And obviously, this would be something that we would be surveying a little bit, right? So if we have this section, here we have a rolling resistance that is going to be equal to 80 pounds per ton. We need to pay attention to the vehicle that we're using and what type of load is sitting on its on its drive axles. So we have to look that up, and I'm going to be kind as can be and not look it up. I'm going to give it to you. Okay. So for this particular vehicle, it has 50% of the weight on the driving wheels. When loaded, and it has 65% gross vehicle weight on the driving wheels when empty. So the first thing that we need to do is take our two sections. We have section A. It has a length. Its length 1,500 feet. Its grade resistance is equal to 0. Its rolling resistance is equal to 200 pounds per ton divided by 20 pounds per ton per percent grade is equal to 10%, right? And in section B, we have its length is 1,500 feet. Its grade resistance is plus 7. We're going uphill. Its rolling resistance is 80 divided by 20, or is 80 pounds per ton. 20 converts it to a grade, and so its rolling resistance is 4%. So the total resistance going from A to B is equal to 10 plus 0 is equal to 10%. And the total resistance from B to where we're done, I guess it would be C, right? B to C, total resistance is plus 7 plus 4. It's equal to 11%. Now, this is typical to have a very high rolling resistance right where you're working because the soil is loose, it's been disturbed, it's being moved around, whereas the 7% is the haul road that comes up out of the pit. And this gets you up wherever you want to be, and then we can drive on a haul road from there. We're just doing a working example. And this is being done, going from A to B and B to C, loaded. But the trucks have to come back, right? So we also have our unloaded grade resistance. We have C to B, and we have B to A. Well, length is still 1,500 feet for both of these. The grade resistance for B to A is still 0, but the grade resistance from C down to B is minus 7, right? It's an assisting slope as opposed to an opposing slope. Rolling resistance, C to B, still 4%. B to A, still 10%. And so our total resistance in here is equal to minus 3%, right? So it's minus 7, but this stays positive whether you're going down or uphill. Then this is now rolling resistance of 10%. So we have two cases. One has a rolling resistance 10%, but here our gross vehicle weight that we need to check is 0.5 multiplied by the loaded, and here it's 0.65 multiplied by the empty load. 0.65 times 74.1 is 48 kilopounds, and 0.5 multiplied by 164,000 is 82 kilopounds. We would check, and this will give us our maximum pull. Our maximum pull, we check with the coefficient of traction. We've done that as an example before, so I want to continue on, but I did want to remind you, you do need to check that. So continuing on, we have our 4 sections. We need to know how well our vehicle is going to do. And in order to do that, we need to go to the manufacturer's data. And in the manufacturer's data, as we fumble around and find it, we will find the operating curves for this particular truck, which I had right here, and now I have very promptly and horrifically lost. And I can see why. Okay, so let's go. We said we were using a 745 articulated Caterpillar truck. We are hauling forward, and all of our grade resistance is positive. So we have two sections, and we need to go to this curve. This curve gives us our rim pull, how much work the tires can do, speed for a vehicle that's loaded or unloaded, as the case may be, with various slopes. So let's start. We have our first section, section A. We're going 10% grade, and we are hauling with a total rolling resistance of 10% because, we have no grade, but our total rolling resistance, rolling and grade resistance is equal to 10%. We're loaded, so we come down the loaded line this way until we hit 10%. Then we come over here, we go along this line till we hit this point, and then we go down. And so our speed is going to be about 14 miles per hour. We're going to be operating in 5th gear. Usually it shows that. I'm not sure why this particular example does not. 5th gear. And we're going to go 14 miles an hour. And we got lots of rim pulls, so we'll be in good shape. So we know how to use that. Our next slope is a 7% grade. It's at 11%, and it's going to be around the same thing. So in this particular case, this was a 10% total. If we do an 11% total, we can come down with 15, that's 11, and then we go over here, and it's a little bit higher than the 10% number, and so we end up a little bit lower. And let's say we're going to go 13 miles an hour. Same gear, looks like, in 5th. So we know those two things. We can now transfer that into our table. So in our going forward table, we have from A to B, we know it's 1,500 feet. We know that our speed is going to be 14 miles per hour. And from B to C, also 1,500 feet, we're going to do that at 13 miles per hour. If we reverse our run, C to B, B to A, we need to go back and look at the curves because we have a different slope here, right? This is now minus 3%, so a net downhill. This one is still 10%, and that's easy. 10% rolling resistance going up, going down, it doesn't matter except the vehicle is loaded differently. So if we go from B to A, we're empty now. We come down on empty, we hit the 10% value right here. It looks like it's in the higher gear, and if we go down, we're going about 22 miles an hour, right? So a little bit faster coming back. That makes sense. It's not as heavy. So then this value for the 10% is 22 miles per hour. A very important distinction because this one is negative. When it's negative, we're going to want the engine to assist us in our braking, right? And the way that we do that is we go to the Brake Retarder Performance Guide. Here's our effective grade. We're doing this empty, same vehicle. So we're coming in empty. We're looking at 4%. Go down here. You can do it in any gear that you want. And it does appear we're going to go about 17 miles an hour. 17 miles an hour because we're empty, and we are in. We're going to be in 8th gear apparently, which would give us our relationship. But that's how we use the brake retarder. So this is going to now be 17 miles per hour. And so we need to get an important conversion factor. The distances are still 1,500. And that important conversion factor is 1 mile per hour multiplied by 5,380 feet per mile divided by 60 minutes in 1 hour is equal to what does that come to be? 5380 divided by 60 is 89.66. We're going to call this 90 feet per minute. So 1 mile per hour is 90 feet per minute. So we can now convert these times. This is how long it's going to take. That's going to be the distance divided by the time is equal to the speed, which means that time is equal to distance divided by speed. And so the time would be 1,500 feet. Our speed is 14 miles an hour multiplied by 90 feet per minute per mile per hour. And that's going to take 16.66 minutes to travel at 1,500 feet. 1,500 feet is about 3/10 of a mile. And if we're going 14 miles per hour, that means in 60 minutes we would go 14 miles, which means we go 0.233 every minute. And if we need to go a number of miles, multiply that by 14, we get that same amount of time. So this is our time in minutes. So we would, what do we use, 14? And so this would be 16.66 minutes. 13, we just do the same thing. If I have 1,500 feet per feet, I divide that by 13 miles an hour, divide that by 90, and I'm not convinced of that number. Hold on a second. Let's take a look. Right, 1,500 divided by 90 is divided by 14. That helps, Kevin. 16.66 minutes is 1.19 minutes. Right? So in this case, the second one, our time is equal to 1,500 divided by 13 times 90 miles per hour, feet per second per mile per hour, and that is going to give us 1,500 divided by 13 divided by 90 is 1.28 minutes. So we can take that 1.28 minutes, we put it up here. Do the same thing with these two other speeds. This is 0.98 minutes. And this is 0.75 minutes, 76 minutes. Now, let's think about what's going to happen. We're going to go up the slope from A to B. We're going to go up B to C. We're going to turn around, dump some soil up there, turn around and go back. And then we're going to turn around and get ready to get loaded. So we have two turns. And we know from experience that a turn is 30 seconds, which is equal to 0.5 minutes. And so we can now put together our truck cycle. Our truck cycle is equal to going from A to B, B to C, turn, C to B, B to A, turn, and that gets us back to the beginning. It's a cycle. We'll write the times down. This takes 1 minute and 19 seconds. This takes 1 minute and 28 seconds. The turn takes half a minute. Returning C to B is 0.98 minutes. B to A is 0.75 minutes. It's flat, so the only thing it's going to control is our ability of the vehicle to push through the soil, and another turn. And we add all of these up, and this gives us our cycle time. And our cycle time is then equal to 1.19 plus 1.28 plus 0.5 plus 0.98 plus 0.75 plus another turn for a half is 5.2 minutes. So a truck starts, we're assuming that it's magically loaded, hauls up the road, dumps and turns, comes back down the road, is ready to be magically loaded again every 5.2 minutes. We can now figure out the number of cycles per hour is equal to the number of minutes per hour divided by the cycle time. So if it takes me 5 minutes to do something and I have a 60-minute hour, I can do 12 of those things. But I don't have a 60-minute hour. I have to use my efficiency in here. So let's say I'm using my efficiency is 50 minutes divided by 5.2 minutes, and I can come up with what that is, and that's 50 divided by 5.2 is 9.62 cycles per hour. And I can go one step further than that. I can say if I have 9.62 cycles per hour, and each cycle was moving 90,400 pounds, then my hourly production is equal to the number of cycles per hour multiplied by the production per cycle. And that is equal to 9.62 multiplied by 90,400 pounds. And if I do that, each truck in that cycle is going to be able to haul almost 1 million pounds, 0.87 million pounds every hour. That's how we do these types of calculations, and it becomes important. Now, there's one other cool thing. I can figure out how much fuel it's going to take me to do this work. So let's go back to our cycle. In one cycle, we have A to B, B to C, C to B, B to A, and we have turns. So we can figure this out. How much work is the vehicle doing? This is doing heavy work, right? It's hauling. This is heavy work. It's hauling. This is C to B. We go downhill, so this is lighter, right? The machine, you're going to use the back pressure of the engine to slow the transmission down. It's a piece of cake. And then B to A, it's light, right? It's just moving itself. And when we're turning, we're also going to be light. And so we can look at the amount of time we had in here. The amount of time we had in here was specifically heavy. We had 1.19 plus 1.28, which is equal to 2.47 minutes at the heavy operation. We also have 3 lights, 0.98 plus 0.75 plus 1.0, because there's 2 turns, right? And so that's 2.73 minutes of our cycle is going to be light. And so if that should, and I'll add up, if you want to check it, that comes to our 5.2 minute cycle. I think that it does. Yes, it does. And so this is our sum, is 5.2 minutes. So if we're told that the vehicle at heavy production consumes 25 gallons of diesel an hour, and at light, it only consumes 6 gallons diesel per hour, our gas consumption when we're operating is equal to 25 gallons per hour multiplied by 2.47 minutes plus 6 gallons an hour multiplied by 2.73 minutes, all divided by 5.2 minutes. And so you see the minutes are going to cancel out, and this is going to give me a result in gallons per hour. So I've got 25 times 2.47 plus 6 multiplied by 2.73 is equal to, divide that by 5.2, and I get an average fuel consumption when I'm operating of 15.0 gallons per hour. And then to account for the fact, oh, I'm sorry, you didn't have any of this on here. I'm sorry. 25 gallons, you spell it as 25 gallons multiplied by 2.47 minutes plus 6 gallons times 2.73 minutes. This is the weighted average divided by the total time, which is 5.2. We'll come up with 15 gallons an hour. That's our fuel consumption operating. In 1 hour, we operate for 50 minutes, right? That's our efficiency, which means we idle for 10. Any of you who've been around diesel equipment, you don't turn the engine off for 10 minutes. It's going to take a lot of time to get back in operation, and it's not good for it. You're better to leave it operating. So we can now do this same thing. So our hourly fuel is equal to 50 minutes operating at 15.0 plus 10 minutes that's operating at light, right, at idle. It doesn't really idle very nicely. And I'll divide that all by 60, and that will give me my hourly fuel consumption in gallons per hour. So I have 15 times 50 plus 10 times 6 is 810, and divide that by 60. I'm getting an actual consumption of 13.5 gallons per hour. If I know that fuel costs $2 a gallon, then I know it's costing me $27 an hour to operate that vehicle. And I'll just show you that calculation, right? If our consumption is equal to 13.5 gallons per hour, and if off-road diesel is equal to $2 a gallon, $2 a gallon, then our cost is equal to the cost per gallon multiplied by the hourly consumption in gallons per hour, and this gives me $27 per hour to operate. So we'll have an example that is like this as well. Obviously, this takes a little bit of thought process, and also takes some information about how we're going to do the haul. So that should be it for this week. And then next week, we're going to start looking at which one of these is more effective. Should I be pushing it 3,000 meters? Should I be trucking it 3,000 meters? Is there another way to do things? Have a great holiday.